Okay. So let's write h hat psi equals e psi. That's our Schrodinger equation, right? So we're going to assume that psi is a function of x times a function of y. Okay? So, and then we're going to write our h into two parts. A part we're going to call h sub, what did I use here? h1. h1 affects only the x variable, and little h2 operator affects only the y variable. So we're going to apply that on psi. What's our psi? It's xy, right? That gives you, so that's your h psi. That's equal to e psi. All right. What do we know about sum of operators? You can apply them separately and then add the result, right? So I can say this is equal to h1 hat xy plus h2 hat xy is equal to e. Instead of writing psi, I'm going to replace it by this by xy. Okay. All right. Now, remember that our operators are linear operators, right? So h1 is a linear operator affecting only the x variable. So as far as h1 is concerned, this function y right here is a constant. And what can you do with constants when you apply a linear operator? You can pull it out. So you can say this is going to be equal to y times h1 hat x plus, okay, let's look at this second expression right here. This h2 hat operator affects only the y variable. So as far as this operator is concerned, this function of x is just a constant. So you can pull that out of your operator. So I'm going to say that's going to be x times h2 hat operating on y. Okay? Because your h2 hat operator is a linear operator. So this thing is equal to e times xy. Okay. I am going to divide. I want to be able to separate variables. So a good trick to do here is to divide both sides of the equation by x, y. What do I get? What's this first term going to be? If I divide this by xy, your y cancels out, right? The x is not going to cancel because that x has been modified by the operator h1 hat. So h1 hat x is not a multiplication, right? So you cannot cancel x. So what you have here is h1 hat x over x plus, what's this second term going to be? h2 hat y divided by y. Your x is going to cancel out. And the right-hand side is going to be, the xy will cancel, xy over xy. So that will just leave you with e. Okay? Let me rearrange this a little bit. I'm going to move my y to the right side. I want to separate my variables, right? So I'm going to say h1 hat x over x equals e minus h2 hat y over y. Now we come into a similar situation that we arrived at when we tried to separate time and space earlier for our time-dependent Schrodinger equation. You have an expression on the left, okay, that would have x, the variable x in it, right? So this depends on x. The expression here will depend on the coordinate x, not big X, but little x. And this is a constant, right? And this expression right here depends on the variable y. So we're again faced with a situation where you have an expression that has x in it, a variable x in it, that's equal to an expression that has a variable y in it. How can those two expressions be equal? How can something that depends on x be equal to something that depends on y? Then the expression itself, okay, both expressions must be equal to a constant. In fact, both expressions must be equal to the same constant in order for both sides to be equal, regardless of what x and y. Remember, x and y are independent variables. For any x I pick, I plug it into the left side. Any y I pick, I plug it into the right side. Both sides must be equal. The only way both sides can be equal is if both sides are equal to the same constant. Both are constant and the same constant. Right? So I can then say that h1 hat of x over x must be equal to a constant. What should I call that constant? Let's call that e sub x. Okay? For reasons that will become obvious later. Now, the right-hand side is also going to be equal to that same constant, right? So the right-hand side would be h2 hat, let's see, what do I have on the right-hand side? I'm going to have h2 hat y over y. Oops, I have to subtract that from e, right? So e minus h2 hat y over y must be equal to the same constant, e sub x. Right? Now I can rearrange this. I can move my, what should I do here? I can rewrite this as h2 hat, I can move that to the right hand side, h2 hat y over y equals what? E minus e sub x, right? But e is a constant, e sub x is a constant, so a constant minus a constant is just another constant. So I'm going to call this, what's a good name for this constant? E sub y. Good name for that constant, we're going to call that e sub y. So here's our simplified problem now. What we had, instead of a differential equation where you had two independent variables, you now have you have x and y, you now have a differential equation that only depends on x, and another differential equation that only depends on coordinate y. So what we have done is we have reduced the problem to a two-dimensional problem into two one-dimensional problems. To summarize, what did we have? Let me see if I have it here. Not there. So to summarize, what we ended up with was two problems. This problem right here, h1 hat x over x equals e sub x, and h2 hat y over y equals e sub y. And how is e sub x and e sub y related? E sub y equals e minus e sub x, or how can I rewrite this? E is just e sub x plus e sub y. All right? Now let's examine each one of these equations individually. What's h1 hat x over x equal to e sub x? Let's rearrange that. What do you get? You get h1 hat x equals e sub x times x. Well, we've seen this equation before. What's h1 hat? It's just the part of the Hamiltonian that depends on x. So that's negative h bar squared over 2m. Now I can drop the partial derivative, right? Since I only have one variable here now. Second derivative with respect to x times big X equals e sub x times big X. That's just a particle in a one-dimensional box problem. Except that last time we called this y as psi, right? And we call this e, right? But otherwise, it's exactly the same problem we had before for the particle in a box. So we already know the answer to this problem then. We already know the solution to this problem. What's the solution? Well, we say psi then is a function of x. Here's your function of x, and here's your function of y. And what's the function of x? Square root of 2 over L1. L is the length of the box along the x-axis, right? Sine n pi x over L1, right? Remember that was your particle in a box wave function, right? Square root of 2 over L sine n pi x over L. So, and then for the function of y, it's going to be square root of 2 over L2 this time, because the length of the box along the y-axis is L2. You're going from y equals 0 to y equals L2. And it's now going to be, instead of a function of x, this is going to be a function of y. And again, you write L2 here instead of L. All right, so function of x times function of y. You'll notice the n here, the quantum number n, I have to label them differently because you're solving these two problems independently of each other. So when you solve one, you come up with a quantum number n. When you solve the other one, you come up with another quantum number. And so to make a distinction between those two quantum numbers, you call one n sub x, you call the other one n sub y. And we already know the restrictions for those quantum numbers. N must be equal to 1, 2, 3, 4, and so on. So for n sub x, we're going to restrict it from 1, 2, 3, and so on. And for n sub y, we're going to restrict it to positive integers, 1, 2, 3, and so on. And we also know the energy already. What did we say the energy was for a particle in a box? One-dimensional is n squared h squared over 8m l squared, right? So we should know that E sub x would be n sub x squared h squared over 8m L1 squared. And E sub y is just going to be n sub y squared times h squared over 8m L sub 2 squared. So problem solved. We have the solution to our particle in a two-dimensional box problem.